function is continuous at x equals 0. Now, if I were just evaluating it at 0, I would just plug it into this function because of the equality. Because I want to know whether it has a jump or not, I have to, because there's the 0, I have to evaluate it at both places. So I have to do f of 0 equals 1 over 0, f of 0 equals 0. Here the answer is 0, and here the answer is undefined. Well, we have a problem. If it's not the same answer on both sides, then it's not continuous. Had I gotten a different real number up here, that would have indicated a jump in the graph. I didn't get a real number. What I got is a vertical asymptote, but that's not a real number either. It's undefined. So since I didn't get a real number and the same real number for both, this is discontinuous. Had it been a real number answer, it would have indicated a jump. In this case, it's probably indicating an infinite discontinuity, but we're not going to worry about that right now because we're only asked, is the point continuous or not? In the next problem, determine whether f of x equals x squared is continuous at x equals 0. Again, we identify this as a quadratic function, so we expect it to be. We do f of 0, and 0 squared is 0. So there's our evidence, and we would say it is continuous at x equals 0. Now that we've looked at how to identify if a function is continuous at a particular point, we're going to look at the next functions to determine if there is any discontinuity, what type of discontinuity. So I look at this first function, and it's they want to know at x equals -3. Well, if I were just finding its output, I'd plug it into this function. But since it's at the brink of those two domains, it's the separation of the two domains for that piecewise function, I need to test it in both. And assuming, okay, if I get the same output for both, then it's continuous at that point. If I don't, then it's discontinuous. So let's take a look. 3 times -3 minus 2, that is -11. That's f of -3. That's in the top function. F of -3 in the bottom function is 2 minus -3, which is 5. These are the outputs on our graph, and they're not the same. This indicates that the height of one is 5 and the height of the other is at -11. So that would indicate a jump. So we would say jump discontinuity at x equals -3. Letter B. They asked us to test actually two values. So we're going to plug these in, but we do want to be aware of what's going on in our function. We see a rational function, so we see this x plus 3 over, and I want this to be x squared minus 9, please change it, x minus 3 by x plus 3. I changed the function for a reason. Because guess what? We're going to have a hole. And when we have a hole, right, it's going to be discontinuous at that hole. And the type of discontinuity is, hopefully you guessed it right, removable. Removable discontinuity at x equals -3. Well, that's one of the numbers we were supposed to test. All right? And if I plugged it in, I'd get undefined. But when I get undefined, I have to ask myself, is it because it was a hole or is it because it was a vertical asymptote? Then when I test this, x equals 3. Okay, plug in x equals 3 into the remaining function, x minus 3. 1 over 3 minus 3 is 1 over 0, which is undefined because there's a vertical asymptote at x equals 3. So since there's a vertical asymptote at x equals 3, that indicates that at x equals 3, we have infinite discontinuity. So remember on the first page we said if it's due to a vertical asymptote, it's infinite discontinuity. If it's due to a hole, then it's removable discontinuity. Here's our last two problems. For the next one, we're going to test these values. We do know that the denominator can't equal 0, so x can't equal 0. That's going to create a vertical asymptote, which we know has infinite discontinuity. In fact, if you do f of 0, you're going to do 1 over 0, and you're going to get undefined. But now we know what it comes from, not a hole, but a vertical asymptote, so we know the type of discontinuity. We're also supposed to see whether it's continuous or not for x equals 1. So we're going to do f of 1, which is 1 over 1 squared, or 1. Since it's a real number output, it is continuous. The function is continuous at the point x equals 1. So it's discontinuous at x equals 0. That is an infinite discontinuity. And at x equals 1, it is continuous. And the next function, I'm going to factor again, x minus 2 by x plus 2. And we see that we have a factor that cancels. So we know right away that we have a hole. And so at x equals 2, we will have removable discontinuity. We also, and that was one of the things we were supposed to check. So we checked that one, we just said it. Supposed to also check 4, so we're going to plug 4 in. Although I also see this factor, and I know that that means there's a vertical asymptote at x equals negative 2. So I can say at x equals negative 2, there is infinite discontinuity because of the vertical asymptote. Oh, and we were supposed to check that value. The only one left that I have not checked yet is x equals 4. I don't expect a problem with it, but we still need to verify that it's continuous. So I do f of 4, which is 4 minus 2 over 4 squared minus 4, or 2 over 12, which is 1/6. 1/6 is a real number, so here's my evidence that it is continuous at x equals 4. So that's part of my answer, right? I have 3 questions here. I'm supposed to check it for 3 different values. 2 of them gave me discontinuity. The hole gave me removable discontinuity. The vertical asymptote gave me infinite discontinuity. The other value I tested resulted in a real number, so it was continuous at that point. Have a great day.